Let f be an extension of E such that there exists an R0 in F and subfield of F obtained by attaching R0 to E turns out to be F. Then such an extension F of E is said to be an simple extension of E. Example: the extension C over R is a simple extension. Well, that's because C is R real, the complex number I attached to R. Well, this requires some checking. Well, that's not difficult because degree of extension of C over R, is 2. So it's not something difficult to check. Well, now let us see for let f be an extension over E and R0 belongs to F. Let us try to see how are elements of R0. So claim, or it's easy to check, or consider K to be those elements of okay, 1 minute, let me reconsider something. Let me define R. Let R be evaluations of polynomial f at R0 where the polynomials f have coefficients coming from E. What do I mean by these evaluations? Well, if fx is, let's say, summation ai x raised to I ranging from 0 to n, since fx, sorry, I need to, it is fx is coming from ex, the polynomial ring, not E. Well, the coefficients are coming from E. So all these ai's here are coming from E for every I lying between 0, 1. Sorry, 0 and n. Now, for such a polynomial, what do I mean by f evaluated at R0? It is just uh, computation of the following expression where x is replaced by r naught. And this is actually an element of f. So elements of r are all such expressions or computations or evaluations. Now, clearly, every element of E is an element of R. Sorry, the wrong notation. Every element of E is an element of R. That is, E is a subset of R. That is because every element of E can be seen as a constant polynomial. So for R in E, consider polynomial FR defined by R itself. So it's a degree 0 polynomial if R is non-zero, and it turns out to be the 0 polynomial is R is equal to 0, in which case the degree is specified to be -1 or defined to be -1. Then when you evaluate fr at any point, in particular at r naught, it is just r by definition, and this turns out to, all such elements are in this set capital R we have defined above. So it means that what we claimed earlier, technically it means that every element of E is an element of R. Now, it's a small little exercise. Check that R is a ring. That's not difficult. So R is a ring which is sitting inside F and which contains E. In fact, it also contains R naught. R naught. That's because if you define g of x to be x, which again is an element in the polynomial ring whose coefficients come from E, then g evaluated at r naught is equal to r naught and therefore is an element of R. Okay. So R is a ring which contains both E as well as R naught. So E union singleton R naught is actually a subset of capital R. Now, R is not just an arbitrary ring. It's actually, since it is sitting inside a field, it's actually a integral domain. So what I can do is consider the the field generated, consider the subfield of F generated by R. What is it again? It is exactly analogous to the above construction that we made. So if you can consider family F of all those subfields of F, K is a subfield and R is contained in K, this collection is again non-empty because because F itself is sitting inside this family F, and then once that is done, what you do is you consider intersection of elements of F, that will be a subfield, and in the sense mentioned above, this will be the smallest subfield mm, subfield containing subfield of F, the smallest subfield of F containing R. So let me henceforth define and denote intersection of elements of F to be uh, KR. So it's a subfield K of F which is generated by R. So let me have this notation. So K subscript R will always denote subfield of smallest subfield of F containing R. So now, since R is contained in KR and KR is sitting inside F, and R we already know, as we saw earlier, it contains every element of K as well as R naught. Let us just focus now on these aspects. K union R naught is a subset of KR. It's a subfield of F. So KR will automatically belong to C that we had seen earlier, defined earlier. Okay, so in that case, the subfield of F obtained by attaching R naught to K is contained in KR. But what are elements of KR? How are elements of KR? Well, KR is actually, I mean, it's not difficult to check again. Look, R is an integral domain, right? So every integral domain is associated or has a so-called field of fractions. So R is embedded in a field called the field of fractions. Because it's an integral domain. Let me call that field of fractions to be R tilde for time being. So how are elements of R tilde? They are of the form R by S, where R and S are elements of R, and S is non-zero. So it is not difficult to check that Kr is actually isomorphic as a field to R tilde. Now, so what are so but then R tilde is actually such fraction, so that would mean that K R naught, sorry, K R contain, it's basically elements of the form F R naught divided by G R naught. That's how elements of R are. So where Fx and Gx are polynomials coming from Ex, and G R naught should not be equal to 0. Okay. But the way we have constructed uh, but then every element of R is an element, I mean but what we know is if Fx is a polynomial, if Fx and Gx are polynomials in Ex, then uh, the way we have then F evaluated at R naught as well as G evaluated at R naught are both elements of subfield E R naught, subfield of F obtained by attaching R naught to E. These are elements of E R naught, and if G R naught is non-zero, then the fraction Fr naught divided by Gr naught is an element of Er naught because it's a field. This is a field. So it will also have multiplicative inverses. Hence, what we see is Kr, every element of Kr, which is basically something like this, which look like something like this, is an element of Er naught. So Kr naught is a subset of, Kr is a subset of Er naught. So with this and what we have seen here, this is wrong. This has to be Er naught. Sorry. You can look back at it and then you can see that it's sorry. There's also a mistake here. It is E. Okay. So thereby elements of Er naught are exactly those of Kr. And what are these? These are of the form Fr naught divided by Gr naught, where F and G are polynomials whose coefficients come from E, and Gr naught is not equal to 0.